All right, here we go. We've got a request to do a halohydrin formation reaction mechanism. And I was hastily setting this up and some typos here already. And some weird stuff going on here. I think we understand what that means. And we have a reaction that creates potentially 4 products, but only one of them is a K, and we have a question. No, I was wrong about that. I'm sorry. So what has to happen first is that we have to remember that water and bromine are mixed previously to the alkene being added to this mixture. And I just want to make sure we have sound and everything going here. Testing. Yeah, it looks good. We have lone pair on water that reacted with bromine long time ago. And that creates a bromine electrophile. Don't get me wrong, bromine itself, Br2, starts as an electrophile. Now it's an even more reactive electrophile. It's got a more electronegative oxygen attached that wants to leave and get its lone pair back. And the other product is Br minus. I'll make it real small because we don't need it. And then the pi electrons are attracted to the bromine. And then water leaves. That's how water gets neutralized. Bromine with lone pairs has the ability to neutralize a carbocation. So if I had just these 2 arrows, I'd be making a carbocation right here. And bromine says no need for a carbocation. I've got a lone pair. As soon as we make our first bond, I can reach over and make a triangle, and it comes back to the more substituted carbon. And we generate this intermediate. It's called a cyclic bromonium. And judging from those products over there, I think the best one for us would be wedge cyclic bromonium. It'll form 50% this one, with both of those bonds being wedges, and 50% both bonds being dashes. You only have to show one enantiomer in a mechanism. And water is both produced and in very large excess because it is also the solvent. The mixture of bromine and water being called bromine water. Now, the triangle intermediate has to undergo what's called a backside attack. And the electrons are attracted to the carbon that spends more time with a positive charge. That's the tertiary carbon. Backside attack means you're coming in 180 degrees away from the bond you're breaking to minimize the lone pair, electron-electron repulsions. And yeah, these pair of electrons are nowhere near these because they're 180 degrees from each other.
So, Professor,
Yes, sir.
when you know when you'd have to do the backside attack?
Oh, if you made a triangle, the next step must be a backside attack. We have about 5 mechanisms where we make triangles.
So every time where you
Every time you make a triangle, the very next step will be a backside attack.
Okay. And that's because of the bond angle, so you don't mess anything up like that, right?
Backside attack is to get electrons away from electrons and relieve the strain of the triangle. Triangles
Yes.
are strained.
Okay.
You got angle strain and torsional strain and other nefarious strains. And here we have cyclohexane with an ethyl. The backside of the bond we broke, a wedge, is a dash. So your new bond to water is a dash, and it's an oxonium, so you're not quite done. I'm thinking about, wait, which product are you thinking about right now? We got one that's real close. I'm just not very happy with the way it's drawn here. It's in a hurry. The H didn't look like an H. And just make it look better. There, that one there is the product we want. And it's the conjugate. Let's see, it's got one less H than the product that we made right here. So it's the conjugate base of this acid. And remember, when you're choosing the best base to grab an H, you should have the one that's got a lower pKb. So choosing between water and bromide, water, pKb is a little lower. It's 14 minus -3, the pKa of hydronium, and that's 17. pKb of bromide is 14 minus -5 is 19. 17 is a stronger base than 19. Please use the water is all I'm trying to say. And you have made this product right here. And we've got a couple explanations to do. Let's look at the grading on this. The grading on this, first of all, this typo's still bothering me here. Yeah, major. And grading goes like this. Now, this might help you when you're studying. A set of electrons like these two gives you a point. This set of electrons here gives you another point. We're up to 2. The intermediate itself, an organic intermediate, is worth a point. We're up to 3. Set of arrows is 4. Another intermediate's 5. These arrows is one more for 6. So mechanism is worth 6 points. Explanation here is worth a little more than normal because we have to explain 2 things. I don't know if 5 points is good. Might be too much. You have to explain why the bromine is on the less substituted carbon and why the oxygen's on the more substituted carbon. That's one thing to explain. And that has to do with the fact that we attacked the carbon that spent more time with a positive charge. I'm gonna say that right now. Oxygen ends up on the carbon. Oxygen attacks the carbon that spends more time with a plus charge. And which carbons spend more time with a plus charge? Ones that are tertiary versus those that are secondary. And I need the magic word in my answer here. Tertiary versus secondary. And the magic word is hyperconjugation. So that explains why the O is on that carbon and the BR is on this. And you've been studying, so you know that what we just described there is called, I don't really need to see this in your answer, but it's called regioselectivity. What atom goes where? Which region does it go to? Selectivity. Now you have to explain why the bromine and oxygen end up on opposite sides of the ring. And that's spatial arrangement. That's called stereoselectivity. So let's go with another color for stereoselectivity. Anti-stereoselectivity comes from a backside attack. It guarantees the bonds will be different. One's a wedge, one's a dash. So if you're breaking a wedge, you have to make a new bond that's a dash. The old bond stays the old bond. It's there. It's there. You didn't break it. So that's why we have anti-stereoselectivity. And I hope that covers what we wanted to talk about to your liking. Does it?
Yeah.
All right. So what do we want to do when we come back?
Maybe another like test problem, something from the test. I'm not sure.
Okay, you find one on a test problem, and I'll be ready to snip it, and we'll start right away.
Yeah, but so it'll be on fall 20. Okay, just like
Okay, I'll have fall 20 open, ready for your request. All right.
okay.
Okay, see you in a few.